properties of inverses. So remember, the last video I kind of went over these, but in general, the property of inverses are the function's inverse undoes the original function. So again, it interchanges what x and y do. So if f of a equals b, so it has the point AB, the inverse will have the exact opposite when I plug b and I get a. So they undo one another. All right, so the outputs of f become the inputs of the inverse of f in the opposite order. And so the domains and ranges interchange. The outputs, the domains, the inputs, the ranges are interchangeable in inverse functions. And so the path is, so again, what the inverse does and why it's important is it gets us back to where we started. If it undoes what we did to something. And so if I started at A, I use my function rules, got me to B, and then if I want to get back to A, well, I use its inverse to get back to A. So the inverse function will take me from B and get me back to A. All right, that's the goal of an inverse. All right, that's why we like inverses, is it undoes, it helps us solve stuff. That's important in solving equations because I want to undo what's been done to an original function. All right, and so again, this is an important property. What's nice about inverse functions is they do have some nice properties. All right, so that's the first big property. All right, so whenever I so again, I get back to where I started. Graphically, what the property of inverse function is, the graph is always reflected over the line y equals x, and we'll look at a couple of examples of graph. The line y equals x are all the points, 1, 1, 2, 2, -1, -1, -5, -5, So that's that line that goes to the origin that splits my plane into two sides. And so when we graph functions that are inverses, they're always reflected over the x, because we're interchanging what x and y do, so it should make sense that it's going to reflect over that line. Because we switch what x and y do, the domains flip. Alright, so whatever was the domain of my original becomes the range of my inverse, and whatever's the range of the original becomes the domain of my inverse. Alright, so they flip, right? Because x's and y's flip. So again, if my function's domain and range of f of x will flip whatever they are. Alright, and so I guess the best way to write up here would be, so suppose my domain was from -infinity to a, my range was from b to infinity. That would be for my original function. That would be f of x. Then for the inverse, it flips. The domain for the inverse would be b to infinity. The range for the inverse would be -infinity to a. So x and y's flip when I do inverse functions because it reflects over the line x equals y. Alright, so this is why it's important that they are one-to-one. Alright, if they're one-to-one, this property and all the properties work. And so it only works if they're one-to-one. If they're not one-to-one, they don't have inverses, but we can sort of force them to be inverses if we pick parts of the function that are invertible, right, where they're either increasing or where they're decreasing. Alright, so we either restrict the domain to give us an inverse, or the original function starts out as an invertible function. And I'll do an example of each and give you what we mean by reflecting across the line x equals y. So look at a couple of examples. So this is the first case where my original function, so the blue function's my original function. Alright, actually the blue function, if I look at it, it does look like it's the cubic shifted up 2 units. So it looks like it's the x cubed plus 2 function, which it is 1-to-1, which makes it invertible. And if you'll notice here, if I pick a point on this line, so this would be the point 1, 3, it is reflected over on my inverse functions. The inverse function would be the cube root of x minus 2, in case you're curious, and we'll explain how we get those later on. It is also 1-to-1, and so you'll notice that this point should be over here. It should match it. On the other side, it should be reflected, and it is. It's the point 3, 1, right? I flipped it, and in this case, the domains are both infinities, and the ranges are both infinities. But it follows that property, and if I pick a couple more points, it still will. This would be the point 0, 2, and reflected over becomes the point 2, 0. Where they intersect, the only time that my invertible functions can intersect is if they're on that line. So the dotted line is the x equals y line, all right? And so they intersect at that x equals line. And so there are two functions that are inverses, all right? Because they're completely one-to-one from infinity to negative infinity. Domain and range are both the infinity to negative infinity cases. All right, the second example is where we restricted the domain. All right, x squared plus 1, and if I look at the entire function, is not one-to-one. So we pick the piece, and we typically do pick the parts that are increasing, although you could technically find where they're decreasing. But we did the increase, and that's usually the rule of thumb, is to go with the increase. All right, so my original function, f of x, is the x squared plus 1, where I have only took the part of it where it's increasing, right? From 0 to infinity. That part, and only that part, is 1-to-1, which means I can find the inverse. And so this case, I'm going to write down my domain and range. So f of x domain, which restricted to 0 to infinity, its range goes 1 to infinity, which means its inverse should be the exact opposite of that, and it is. If I pick a point over here, so this would be the inverse function. All right, so the inverse function, if you want to know what it is, the inverse function is the square root of x minus 1. Right, the square root of x minus 1 is the inverse, and we'll explain how we find that in a little bit, but that's what it is. If I pick any point on this line, it should be reflected over the line x equals y, so that green one is my line x equals y, which is they are reflected over. Right, I've labeled 4 points here. And they all will reflect over this line. So this is the point. This first point is the point 0, 1. Well, it reflects over, and here becomes 1, 0, and that's true. This is the point 1, 2. Well, it reflects and becomes 2, 1, and that's true. This is the point. Again, that one's kind of in the middle, but it does reflect over there. That's in the same spot. And the next point is 2, 5. Reflects and becomes 5, 2. Right, and it would be true for any point on that line. And so when we look at the inverse, f of x inverse, its domain is from 1 to infinity, which was the range of the original function. Its range starts at 0, right? Starts here at 0 and goes up 0 to infinity. And so those did flip, right? It does follow the properties. Now, we weren't able to look at the entire function, but we were at the very least able to determine, we were able to restrict it, and again, we typically restrict it on places where it increases, and in that case I could find the increase part, and on that part it does have an inverse, and only on that part does it have an inverse. Alright, we will stop there. I'll pick up the test we used to make sure that we actually found inverses.